Example 3. Let the short-run production function be Q is equal to 70L squared minus 0.8 L cubed. Find the value of L which maximizes average production. Now this function might be familiar because we did use it in the concept videos. However, we were maximizing production. Here we're trying to maximize average production. So we are going to have to manipulate the function before we do our optimization. So this is what we optimized in our concept video, but now what we're going to optimize is going to be our average production. And average production is going to be our production divided by our total labor, production per labor, or average production. So I take my 70L squared minus 0.8 L cubed divided by L, and what I get is 70L minus 0.8 L squared. And this is the function that I am going to aim to optimize this time. Sometimes you might be interested in maximizing production, sometimes you might be interested in maximizing average production. Now to do this, I'm still going to follow my classic optimization process. I'm going to take the first derivative, dAP by dL, of this function, and I'm going to have 70 minus 0.8 times 2 gives me 1.6 L. I then set this first derivative to be equal to 0, and I solve for the L values. So I'm going to move L over to the other side by adding 1.6 L to each side. So that 1.6 L cancels out on this side. I get 70 is equal to 1.6 L. I then divide both sides by 1.6 so that the 1.6 cancels out. And I'm left with L is equal to 43.75. So this is the L value at which I will have my first derivative equal to 0. Now let's see what that associated average production is. Average production when L is equal to 43.75 is going to be equal to 70 times 43.75 minus 0.8 times 43.75 squared, giving me 1,531.25. Now before I get all excited that this is the maximum average production, I should confirm that it is indeed the maximum production. For that, I'm going to take the second derivative, d squared AP by dL squared. So I'm going to do the derivative of our 70 minus 1.6 L that we have over here, our first derivative, and I get negative 1.6. So my second derivative is negative everywhere, indicating that it is concave down everywhere. And because our first derivative showed that the slope was equal to 0 right here, I can see that this is indeed a maximum. So I've solved this problem. I know that I have maximum production when L is equal to 43.75. And furthermore, I know that that average production, that maximum average production is 1,531.25. The optimization is done. Let's see if we can graph this function as well. So I know that this function has one maximum value. I'm going to see if I can find the intercepts now. Let's recall that when L is equal to 0, I should be able to get the vertical intercept or the AP intercept, as I will be graphing AP versus L. So subbing in L is equal to 0 into our equation, I get AP is equal to 70 times 0 minus 0.8 times 0 squared. This is my original AP equation that I'm subbing into. And what I get is AP is equal to 0. So I have a coordinate 0, 0 right here. Next, I'm going to look for the horizontal intercepts. That's going to be when AP is equal to 0. I'll get my L intercepts where I cross that L axis. So I'm going to set AP is equal to 0, and that's going to be equal to 70L minus 0.8 L squared. And I'm going to solve for L. I'm going to factor this, so I can factor out L. So I have 70 minus 0.8 L times L. And if either of these terms are equal to 0, then I should get a product that's equal to 0. So this will happen when L is equal to 0. We already solved for that, our 0, 0 intercept over here. As well as when 7D minus 0.8L is equal to 0. Doing a little bit of algebra, I'm going to move my 0.8L over to the other side. Let's give myself a little bit more space. 70 is equal to 0.8L, and then I divide both sides by 0.8, and I get L is equal to 87.5. So I know that when L is equal to 87.5, my AP, or vertical axis, value will be 0. So I'm going to put that right here at 87.5 for my L value. And 43.75 is halfway between 0 and 83.75. I had a value of 1531.25 for my maximum average production. And so from here, I just draw this dome-like quadratic. And it should look something like this. Looking through our graphs, I see two that have this concave down quadratic shape, and that's A and H. When I look at H, I can see that the intercept with the vertical axis is lower than 0. So that cannot be the graph that we just produced, as there was an intercept at 0, 0. That can be found in our graph A. Furthermore, I can see that my maximum is when we have 43.75 on the horizontal axis and 1531.25 on the vertical axis. It doesn't go as far along the horizontal axis as the graph that we drew, thus it doesn't cross that horizontal axis again, but graph A is the one that matches with this equation.